Now, in this video, I'm going to tell you a special phenomenon that the image position of an object in water is not fixed. Well, very often in DSE physics, we regard the image of an object as something fixed. For example, if this is a plane mirror, we have got an object O. In fact, not only regard. All the rays emitted from the object after refraction will appear to come from a fixed image point. Okay, a fixed image point. So this is the image. Okay. Whatever position you look at it, here, whatever position, you find that the image is at that position, right? The reason is simple. Suppose this is the mirror. This is the mirror. And we got an object O, and we got an image position I, which is equally distant from the mirror. Then at any point on the mirror, if we join this point with O, join this point and I, we get two congruent triangles, SAS. So these two angles are equal. If we produce IP, right? We produce IP. Then a ray from O hitting P is reflected this way. Why? Because these two angles are equal. As a result, these two angles are equal. So this ray obeys the law of refraction because these two angles are equal. So this diagram proves this result. However, this is not the case for an immersed object. Now, if we use this idea to find the image of an immersed object, right? So suppose this is water, this is air, and we got an immersed object here. Well, this is the light, the ray emitted by that object directed normally. So it will be reflected undeflected. So if it direct another way, which makes an angle R with the normal, then the reflected ray goes like this. So this is the angle I. So if we produce it backward, it will cut the normal at this point, say G. This is I. Now, if the image point is fixed like this, this will be the image of F. Okay. However, there is a question on this. Only one question in the past 40 years. It comes from 1984. Okay, this is from 1984. HKCE, multiple choice. It's question number 16. Question number 16. So it says that if we got a fish here, and we got an observer eye here, the line joining the fish and the eye makes an angle of 45 degrees with the water surface. The question asks us to determine where should be the image position. Should it be Q or R? Okay, the other is not possible. STP is not possible. Now, if we follow the reasoning, if we regard the image as something fixed, the image will be vertically above the fish, so it should be, the answer should be Q, which is B. Let's look at the answer. Let's look at the answer, which here, number 16. The answer is C. Okay, C is out. It should be this point, not directly above it. Not directly above. Let's see why. Why it is so. Let's see why it is so. Now, the essence of the question lies here. What happened when R increases? When R increases, what will happen to the point G? So when R increases, what will happen to G? Okay. Now, according to the principle of light traveling from dense to rare medium, it bends away from normal. So let's look at it. If the reflected ray pass through G, it bends away from normal. If the reflected ray cut the vertical at the point above G, it is also bent away from normal. So bend away from normal alone cannot determine where the reflected ray should be. So this must be done by calculation. Okay, let's do that calculation now. Let's do that calculation now. So here we have the water surface. Okay, here water surface. This is the point F. Well, say it has got a distance D from it. So this is the angle R. This is the angle R. Well, if it hits the water surface at the point X from this point, and then it bends away from normal, which cut the vertical through F at the point G. Okay, we got this point Y, and well, this is the angle I. This is the angle I. This is the angle R. Okay, so we call this hypotenuse here, we call it T. For this hypotenuse here, we call it S. Right? So we apply the Snell's law. Snell's law tells us that the refractive index eta, or sometimes people say it N, eta is equal to sine I over sine R. So what is sine I? I is this angle. It should be X over T, isn't it? What is sine R? R is this angle. So sine R is X over S. Right? Simplifying. So eta is equal to what? S over T, isn't it? S over T. S over T. So in other words, T, this side, is equal to S over eta. Right? But what we are doing, we're trying to see the trend of Y. What happened to Y? Will it decrease and R increase? Okay, so we form an expression for Y. Now we've got a right angle triangle here. So Y square is equal to hypotenuse T squared minus X squared, isn't it? So that's S square over eta square. So X square can be written as eta square X square over eta square, right? Now, S is the hypotenuse of this right angle triangle. There's right angle side, X and D. So Y square is equal to S square, which is D square plus X square, okay, over eta square, and then minus eta square X square. Okay, doing a bit of arrangement, so Y squared is equal to D square minus eta square minus 1x square over eta square. Isn't it? So this is a positive number. This is a positive number. So as what is x? X is equal to what? D tangent theta. Okay, D tangent r, isn't it? Why choose D not S? Because D is a constant. All right. So as r increases, x increases, x square increases. So eta square minus 1. Now eta is a number greater than 1. Okay. Eta square minus 1 times x square increases. So as a result for this fraction, this is constant, this is constant. This increases. So the whole fraction, which is y square, decreases. Okay. Minus something more. As a result, y decreases. So we've established the relationship. So when r increases, y decreases. What does that mean? If we increase r, the refracted ray will cut the vertical through f at a higher point. Okay. Now, having that we can draw this diagram. If we increase r, the refracted ray will cut the vertical through r at a higher point, say G, not G, say H, okay, high point H, right? So what does that mean? That means each R will have the refracted ray produce cutting the vertical at the point, and when R increases, that point increases. That means for whatever R, it will cut the vertical at different points. So as a result, look at that. These three rays, they are not concurrent, not as beautiful as that. They are not concurrent. So if we are straight, the image only exists when all the reflected rays are concurrent. This doesn't happen. There is no image at all, right? Because these two rays meet at here, reflected ray meet at here, and these two reflected rays meet at here. These two reflected rays meet at here. Okay, there is no reflected ray at all. However, if we put an eye above the water, we do something. We do see something. Okay, so we should define the image position more flexibly. Okay, so the problem is that you don't find an image position. Is that you are taking too much rays. If you restrict your number of rays, because you need two rays to form an image. Okay, now in order to make it suitable, we restrict the rays which can go through the eye. How to do that is to, for example, this is ray R1. We draw another ray R2. Say R2. This is R2, which is this is R1. This is R2, which is close to R1. Okay. As a result, of course, the point will higher. It will the reflected ray will cut it at a high point. Say we call it what is point? J. Okay, high point J. So the image, be careful. The image as seen by this eye. So the image of F when an eye is on the path of R1. How to define that? We want as little ray as possible. So ideally, it's if there is something called the next ray, the neighboring the next ray is all right. But however, there is no neighboring rays. Okay, no matter how close there's a gap between the two ways, and there are rays between them. So in mathematics, we have a way out. Okay, that the intersection point is J, so it's the J, but we take the limit as the ray R2 tends to R1. Okay, so the image position is defined to the limit of the intersection of refracted rays of R1 and we call it very close. We call it well, this term comes from calculus, infinitesimally closed. No past tense. Infinitesimally close ray R2. Okay. Okay. In mathematical symbol, it's R2 tend to R1. Right? Now we got the definition. Okay, and that can be done mathematically. Okay. Similarly, if we put the I here. Well, this is in fact in the layman's language is the intersection of the refracted ray of R1 and a very close ray R2. So similarly, if this is ray R3, what is the image? We choose a very close ray R4 and find the refracted ray. Say if the refracted ray is here, meets at K. So image of what? This time is of R3. Okay, it should be image of F when an I is on the path of R3. Okay, just simplify as that. It's the limit. Well, they R3 and R4 they meet at K. Okay, it's the limit of the point K when R4 tends to R3. Right? Now, up to this point, we can okay, we'll continue in the next video, in which I'll show you how to do that mathematically, and also I'll solve the MC question.